Welcome back, class, and we are still on chapter 1, obviously, and I think we covered slide number 24 at the end of the last recording. So now I'm on slide 25. I have to do a few more slides of theory, and then we'll also look at some problems in this recording. So far I've shown you this this format for describing a traveling wave, sinusoidal wave in a lossless media. Now this format was actually from a different textbook. Now let's start looking at how our textbook is showing the same thing. And what you'll notice immediately in section 1-4.1 is that the way we are shown the waveform, it's in this format. So there is y instead of p, y as a function of x and t. T is time, x is wave distance. The amplitude is shown as a, and then there's a cos, and for omega our textbook shows 2 pi by t. For beta it shows 2 pi by lambda, and then the phase angle phi 0. Okay, so a is the amplitude, t is the time period, lambda is its spatial wavelength, and phi 0 is a reference phase. Okay, so there is definitely some useful information in the way our textbook describes all this. So it'll definitely be beneficial for you and for me to spend some time looking at the various relationships, etc. I mean, most of this we have seen, so nothing should be new, but at the same time the way he describes it is pretty nice. So for example, we have seen the omega definition, the beta definition. When phi 0 is 0, then this becomes like this, a cos omega t minus beta x. So we have seen this relationship also. This I like, these two graphs on the right side. They tell you how to plot and how to think about this waveform, right? The one we just saw, either this or this, on slide 25. If you look at slide 26, first he takes time to be 0. That means at t equals 0 time, and we'll assume this is a small lake or a pond, and you just threw a stone in the middle and you see the waves going out on the water. If you look at time 0 and you look out at the wave, what you're seeing is the distance away from the stone, right? And you'll see that the waves are like this, and they are sinusoidal in nature. Now at time equals 0, meaning only one instant in time, right? So you can't capture all these details, but maybe you and 3 or 4 of your friends can stand and say, you look here, there, you look there, you look there, and I'll throw the stone, and what do you find? And you'll be able to plot this. So that's what it means for t equals 0. Similarly, you can say, I will only observe one point. That means the center point where I throw the stone, and ignore the rest of the lake. But at that one point, and that point is at the origin, that means x is 0, you're looking at one point, but you're going to look at that point slightly before you throw the stone, then you throw the stone, and then for a few seconds after you throw the stone. And if you see that one point, which is at x equals 0, you will also see that the peaks and the dips of the water at that point follows a sinusoid. So that's one simple way I imagine, looking at these two graphs. At t equals 0 and at x equals 0, how do you plot this? Because as I've told you before, this sinusoid is in two independent variables, t and x. The dependent variable obviously is this y or this p. Okay, so the rest of it I think it's easy enough to understand. And here also in this slide there's not too much that's new. Of course, we start defining what is the positive direction. So this direction we consider is plus, and I'll leave you to read all this. But this relationship again is important, wave or phase velocity or propagation velocity, that he shows as mu p or up instead of vp. Up is frequency times wavelength, or another relationship is omega by beta, and both these are important and we use these a lot in problems. Now if this is sound or light, then we are talking about not up but c or cs, right? Alright, so last thing before we move to lossy media, I think a couple of more things. One, wave moving along x direction or minus x direction, wave moving along plus x direction, positive or minus. So there's a rule here, if one of the signs of these two coefficients is positive and the other is negative, then that wave is moving in the positive x direction. If both omega and b have positive signs, the coefficients are positive, then we say wave moves along negative direction. Okay, so that's something to remember. It might appear as a question later on. Here he tries to describe the importance of the phase angle phi, right? And this is not new to us. I think we should all be familiar by now, but you can spend some time making sure you understand. As I always say, this side is always earlier time. Any point you pick, you can say left is earlier, right is later and in the future, right? So with that, you can see that the red wave, he is using the blue wave as the reference wave, and then he says the red wave leads because it's ahead in time, and the green wave lags or it's behind in time. Okay, and the phase angle for each is the magnitude is pi by 4, right, which is 45 degrees. So nothing new. I hope by now you're all familiar with this. If not, spend a few minutes becoming familiar. Okay, so we have some examples and problems to look at, but I'm going to skip this for the moment. Let's finish the theory and then we can come back. Here's another example. Here's another problem from the back, so we'll come back to that. But there's one or two more topics that we should cover in the theory, and then we'll come back for the problem. So this is the next section, 1-4.2, and here we are talking about waves in a lossy medium. That means previously we called it lossless. That means the waveforms never die, they just keep going forever. But here we have things like friction and other forces that try to destroy or kill off or end the waveforms, right? And the general equation for such a waveform in a lossy medium for a traveling wave, it has this new factor exponent with a negative sign, right? And so here's a good example of how a waveform in a lossy medium behaves. I'm happy he showed us this nice waveform, and he shows this equation for just the attenuating factor. It's called, which is 10 e to the power minus 0.2x. It's also called the wave envelope. So in a lossy medium, the wave's amplitude decreases as exponent minus alpha x. That's the new thing to remember. This exponent minus alpha x is called the attenuation factor, and alpha is called the attenuation constant. Attenuation means reducing, forcing something to reduce is the English definition of attenuation. So this is the only one slide we have for the theory on the lossy medium on slide 33. And with that, we have a problem next, a couple of problems, so we'll come back in a minute. Okay, what else do I have in theory? So there's a section called Review of Complex Numbers, and there's another section called Review of Phasors on slides 36 and 37. And I'm going to skip most of this because everything here is what we have already done in our first two courses on circuits. So nothing new that I can teach you, but I just brought in a problem, so maybe we'll look at one problem quickly, because you may remember, or you may have forgotten like somewhat what we did, because last semester I think maybe you didn't have any course that dealt with this stuff. So just to refresh your memory, I may do a couple of problems and I may give you some homework problems, but the theory of this, both for complex numbers and phasors, there really isn't anything too new. Having said that, let me point out that one thing I notice in the textbook is that he uses this format a lot. We are more used to using the first two formats, right, for complex numbers. But here he uses this, which really is not new, we've seen it, but you may run into this format a lot more than previously. Okay, lastly, I have one slide on review of phasors. And again, as I told you, he likes this format. So he writes this phasor with a tilde on the top. And most of these we should know by now. There's nothing new, except maybe this third and fourth format, because here previously we only dealt with t as an independent variable. Now we have t nx, and you can see how that's written in phasor form using the exponential form, right, in phasor terminology. Everything else we should know by now. So one little note he has that says if we set phi phase angle equals 0, then this is written in this way. And he also makes the point that depending on the sign of the exponent, the wave is either traveling in the negative direction or a positive direction. Okay, so if the phase constant beta here is given by the negative exponential, that means it has a negative sign, then that's traveling in the positive direction and vice versa. Okay, thus the sign of x in the exponential is opposite to the direction of travel. So that's one thing to watch out for. And then I have a problem which is pretty simple. I'm sure you guys can all do this in your sleep, I hope. But I will maybe look at this just to refresh your memory. Okay? All right, so that's the last slide. So let's go back and start looking at some numerical examples, because that's what we like to do, right? Solve problems on all this theory. This we already talked about on slide 24, so I'm going to not look at it again. I'm moving ahead. Okay, so this is slide 30. Now there are two types of problems, well, there's three types of problems in the textbook. One is what's called an exercise that he gives us frequently, and this is exercise 1-2. For exercises, he gives you the answer right there on the same page. Okay, so this is something I'm going to skip and I leave it to you to do it. I advise you to do these. There's many of them scattered throughout the chapter. They are a good way to refresh your understanding of the theory, and the answers are right there. If you can't solve something, you can definitely come to me and I'll help you, but it's to your advantage to try and solve these by yourself at various points as you're reading the text or you're going through my notes. This one thing, I'll just solve it quickly. It's a pretty easy one, so no big deal. But what is being asked is, the red wave is the reference wave, and it's given by phi cos 2 pi t by 8. It's a little confusing how he writes it, but it's actually 2 pi by 8 t. So that's the red wave. Then he's given 4 equations and he says, A, which of these equations applies to the green wave and which of these equations applies to the blue wave? So how do you solve something like this? So here's my solution. Now t is 8 seconds, right? T is the time taken for one complete wave. Positive back to positive, that's 8. So t is 8 seconds because this is in seconds, which is 2 pi radians. We know that one complete cycle means 360 degrees or 2 pi radians. So 1 second is pi by 4 radians. So take red wave as the reference. Green wave is 1 second leading, right? Green wave is behind in time, ahead in time, that's why it's in this direction. The blue wave is in this direction, so it's lagging. So the green wave is 1 second leading, which is pi by 4 leading. So you have to write with this plus pi by 4 sign. Remember, leading always gives you this plus phase angle. Next is the blue wave, which is 2 seconds, right? The difference between 2 and 4 is 2. So the blue wave is lagging by 2 seconds, and 2 seconds means pi by 2, because 1 second is pi by 4, 2 seconds is pi by 2, it's 90 degrees. And so how do you write that? V equals phi cos 2 pi by 8 minus 90, which is phi sine 2 pi by 8. So this is a little tricky because you have a something minus, cos of minus something is sine of that, right? So that's why 4 is like that in sine. Okay, so I hope you understood this, and again in the future I'm not going to do too many of these exercises unless there's a very good reason to do it. Mostly I'm going to leave it to you, and please make sure you solve them. They're for your own good. Okay, similarly there are examples in the chapter. Same rule that we saw in previous textbooks. An example is something that the writer of the textbook, he has solved it and has given us all the individual steps. So here is an example. Again, because the solution is so clear, I don't think I need to spend any time. But generally, I look at an example, I see if there's some important point I can tell you that will make it easier for you, I may tell you. Otherwise, I'll leave it up to you to spend a lot of time and energy going through each step, making sure you understand, and then improving your knowledge. Then I have a problem which is from the back of the chapter. Now this of course I will do in detail, but example like on slide 31 or exercise like on slide 30 generally is for you to do. Okay, alright. So let's quickly look, having said that, let's quickly look at example 1.1 just to see what is asking, what is given us. So there's a sinusoidal sound wave traveling in the water. Wow, that's nice. In the positive direction. So the amplitude is given and the actual value of the function was observed to be at its maximum value at t equals 0. So at t equals 0, the amplitude was 10 is what he's telling us. And at the same time, it's t equals 0 and x equals 0.25. Some other data is also given. The frequency is given in hertz, kilohertz, and then the wave velocity is given as 1.5 kilometers per second. So using all this, he's asking us to develop a relationship formula Pxt. Now we know the general form is Pxt is a cos this minus plus phi, right? So we have to find all these. We have to put in the value of a, put in the value of t, put in the value of lambda, and phi 0. So how does he solve it? You can see it by yourself. He uses these nice formulas. For lambda, he uses mu p by f. He gives us mu p, so it's easy to find. Frequency is given, so t is easy to find. then to find phi 0, he uses the fact that we know the actual value of p at one point, which is 10, and that point is t equals 0, x equals 0.25. So if you plug all that in, you easily get an expression for phi 0, and that turns out to be pi by 3, and he creates this relationship. Okay? All right. Next, we'll look at a problem from the back of the chapter. So for this we have to go to my PDF, and I'll open that in a second. But let's see what the problem is. So the problem gives us two waveforms on a string. One of them is y1, one of them is y2, and they are shown one with a plus and one with a minus, and then even there's a sign difference in the middle for their coefficients. So x is given in centimeters. The waves are said to interfere constructively when they are superposition. When you add the two, y1 and y2, if the magnitude is a maximum, then we say constructive. Destructive means the opposite, when the magnitude of the sum is minimum, right? So he's telling us that. Now he's asking us, part A, y1 and y2, are they traveling in the positive direction or negative direction? Number 1, part A. Part B, at a certain point in time, at what location x do the two waves interfere constructively, and what is the corresponding value of the magnitude of ys? Also, at that same time, t equals pi by 50 seconds, at what location x do the two waves interfere destructively? That means when is the sum of the two a minimum? And what is that corresponding minimum value of the magnitude of ys? So that's what is being asked. Let me go to my PDF. Here it is. It's on page 1, and this is handwritten, so I apologize. My handwriting is never the best, but hopefully I can walk you through this and you'll understand. So I've written y1 and y2 as given. Since the sign of the coefficients of t and x are different for y1, right? The sign here is negative for x and the sign for t is positive. If they are negative or different, not the same, then we can say that wave is traveling to the right or in the positive direction. Similarly, the other wave you can see has the same sign, so it is traveling left or in the negative direction. That's the answer to part A. Part B, we have to take a time of pi by 50 seconds and we have to calculate ys, right, which is the sum of y1 plus y2. So ys, you plug in this value. We don't know what x is, so we just leave that. We have to solve for x actually. So you get this expression, and this is in the form cos x minus y minus cos x plus y, and that in trigonometry is 2 sine x sine y, right? You know that. So ys can be written in terms of a sine function as this. Here you can calculate this value, sine 0.4 pi, that's a constant number, but make sure you put your calculator in radians mode, right? Because we want to calculate this in radians, not in degrees. If you want to convert to degrees, then this pi becomes 180 degrees, right? Then you can convert. But if you want to use pi to solve on your calculator, make sure the calculator mode is switched to radians. Okay, otherwise you will get an error in the answer. Okay, so anyway, this quantity sine 0.4 pi is 0.95. Remember, the value of sine or cos can only go between 0 and 1, right? So in this case, it's 0.95. And so if you solve this for x, you get ys as an equation like this, 7.6 sine 30x. It's a simple sinusoid, right? Okay. Now continuing on, we have this relationship. Now we have to find the maximum value of the magnitude of ys. So if you take the magnitude of ys, it doesn't matter that sine can go, actually sine of an angle can go from -1 to 1, right? -1 to 0 to 1. So even if this angle is minus, the magnitude will still be, the maximum will be 7.6. So even if you take -1 here, that becomes minus 7.6. But if you take the magnitude, that means you have to ignore the sign, you get 7.6. Similarly, the minimum value, it can go negative, it can be minus 7.6. But once you take the magnitude, it becomes plus 7.6 again. So that is the maximum. So the least value, minimum, is actually 0, not minus 7.6 as I wrote it here. So the maximum was 7.6, the minimum was 0. And we can say that only because we are only being asked to find the magnitude, not the real value, right? Okay. So max when sine 30 equals 1, right? This whole thing when it's 1. And that happens when this value 30x is either pi by 2 or, plus n pi. Because we know that sine value at every 180 degrees or multiple of 180, it repeats, right? So x equals pi by 60 plus n pi by 30 for all n equals 1, 2, 3, 4 and so on. Similarly, minimum sine 30 equals 0. So 30x equals 0 plus n pi. So x equals n pi by 30 for all n equals 1, 2, 3 and so on. So for these values of x, pi by 60 plus pi by 60 plus pi by 30, pi by 60 plus 2 pi by 30 and so on, you'll find the maximum or constructively adding superposition. The minimum is destructively adding, that happens at these x values. Okay. I hope that was clear. If you had any questions, let me know. Okay, I gotta move on. Now we have an example from the textbook, example 1.1-2 on lossy media. That means the wave is going through a lossy media, which means we have a attenuation factor e to the power something. And so this problem is about that. This example, it's solved in the textbook, slide 34, and then I have slide 35 where I will, this is from the back of the chapter, so we'll look at it on my PDF. So let's look at slide 34 first. He's given us a exponential function, exponential sinusoid, and this is obviously in this format. It's in a lossy medium, and he wants us to do things about the exponent and the alpha, right? So first of all, determine the direction of wave travel, wave velocity, and the wave amplitude at a distance of 200 meters. That means at x equals 200 meters, find the wave amplitude. So here's the solution. First, he gives us the direction as in the positive. Wave velocity, he uses this. This is a laser beam, so it's not sound, probably close to light. Yeah, you get the answer for light because a laser beam is light, right? So he shows you that if you do omega by beta, you should get 3 into 10 to the power 8, which is equal to c, the velocity of light in free space. Lastly, in this formula, if you put x equals 200 meters or x equals 0.2, 200 meters, because this is all in meters, so just substitute 200, then you should get E, the value at E, and also x equals 200 here. Remember, even this exponent function carries an x. So if you put the x value 200 in both and you calculate you are only interested in the amplitude, right? So we are only worried about this. Sorry, you don't have to put it here. We are not being asked to do the whole function. Only this function with x equals 200, so which is what he does and comes up with 0.37 as the value of E. Okay. All right. So I won't spend too much time on that because we need to look at 35. So what's on slide 35? What is this problem? Problem 113 from the back of the chapter. So the voltage of an electromagnetic wave traveling on a transmission line. So this is some kind of line, maybe a copper line, is given by this value, where Z is the distance in meters from the generator. So instead of using X, he's using Z here. Again, find the frequency, wavelength and velocity of the wave. Then at a certain distance, 2 meters, the amplitude was known to be 2 volts. So find alpha. It's exactly the same. Yep. Okay, almost the same, but not quite. Here the amplitude is given. Previously the amplitude was not given, just some distance was given. Here he is asking us to find alpha. Previously alpha is given as 0.03. But here we don't know alpha and we have to find it. Okay. Alright, so let me open my PDF and look at example 113. So I wrote the original equation given to us. From here you can easily tell omega and beta, right? This is omega, this is beta. Find F, lambda and Vp, velocity. So frequency is W omega by 2 pi, 2 gigahertz. So this is certainly not a power frequency because power frequencies are only 50 or 60 hertz, right? Lambda equals 2 pi by beta, so that's wavelength is 0.1 meter. Velocity is omega by lambda, which is 2 into 10 to the power 8. So this is not the speed of light, but it's pretty close, right? Because speed of light is 3 into 10 to the power 8. Lastly, at z equals 2 meters, we are given that the amplitude is 2 volts. That means 2 volts equals 5 exponent minus 2 alpha, where 2 is the x or the distance. So solving this, we get 0.4 equals this. Taking ln, natural log on both sides, you can write this as minus 2 alpha equals ln 0.4. I hope you know how to do this. Please make sure you revise your mathematics to know this. And then you get alpha as 0.46 Np per meter. Okay. Alright, so that wasn't too difficult, but I hope you followed every step. Okay. Now, what else do I have left? So I have review of complex numbers and I have review of phasors. Now, like I said before, I certainly hope by now, and I'm sure all of you are pretty comfortable with complex numbers and phasors. After all, we did the same stuff in EE 188, then we did EE 280 where we used these ideas. You guys also did, I think, a course on signals and systems, Fourier series and all that. I'm sure you've used these pretty same concepts in those also. So there's not really too much I need to do, I think. But having said that, I thought at least let me solve one problem each and then assign you some homework so you can work on them on your own. Okay? I think that is enough review of these two topics. Alright, so problem 118 from the back of the textbook says two complex numbers are given, Z1 and Z2, in rectangular form. And so in polar form, we have to find Z1 times Z2. This is actually a multiplication, so maybe I should do that just to make it clear. Then there's a division, Z1 by Z2 conjugate. I hope you know what a conjugate is by now. Then there's Z1 square is something to be found. And then there's Z1 times Z1 conjugate again. Okay, so these four things to be found. Okay, like I said, in the textbook he tends to favor using this format, although he uses all three, no doubt, but much of his theory is around using this. So we may have to become more comfortable with that terminology as we go through the course. Okay, all right, so let me go to the solution of this. You should be able to do this pretty quickly on your calculators. You don't need me. Anyway, Z1 is given, Z2 is given. I immediately converted it to polar form and it comes out with this silly root sign, but anyway, root 13 and root 5, and then the angle is 146 and minus 63. So Z1 times Z2, you know how to do that. You multiply these two, so that's root 13 times root 5 becomes root 65, and then you take the sum of the two, right? So 146 and minus 63, if you add it together, you get 83. Similarly, Z1 divided by Z2 conjugate. So Z2 conjugate means first you have to flip the sign from minus to plus, which is what I do in the denominator. And then to do the division, you do root 13 by root 5, which I just leave it like that. And the 146 minus 63 is what you put here in 83, which is 83. Similarly, Z1 square, you square this whole thing. And the trick, you may know this or you may not know this, you can actually put it into a calculator, it will do it for you. Obviously root 13 just becomes 13 when you square it, but this, the angle inside the, in the polar form, you just double it when you do a square, right? It becomes 2 into 1/4, which is 292. Maybe you remembered that, maybe you didn't, but hey, here it is. Lastly, Z1 times Z1 conjugate, which is root 3 times 146 into root 13, into root 13 times minus 146. You have to add the two so that it becomes 0, so the angle becomes 0, and you get root 13 into root 13, which is 13. So what this teaches you really is, when you do a product of a complex number and its conjugate, then you're left with just the square of the magnitude alone, right? So magnitude was root 13, that square of that is 13, which is what you get here. So that's, I guess, a lesson we have learned also. All right, not much there to talk about, I hope, by now. And the very last problem I have, I guess we have seen this slide. I showed you that this format is something new for us because we have introduced this beta x now, the distance parameter. So that converts to this in polar form. So just keep that in mind if we run into problems in the future. Okay. So one simple circuit he has given as a problem in the back, and I thought I'd solve it just to show you and refresh your memory on basic things like Ohm's law and voltage division and current division, and how to convert from R or L when there's an alternating input, AC signal, from L value to impedance value. So that's something also to remember, right? So all those are in this problem. I'm going to just quickly walk you through it. I might give you a problem to solve just to refresh your memory. And I think we may have to use all these techniques on phasor arithmetic later on in the course. Okay. So what is the problem here? Again, 129, there's two resistances, there's one L. The signal is a alternating waveform, the magnitude of 25 volts and a phase angle of minus 45. omega is 4 into 10 to the power 4 radians per second. Find the current here. Okay, so you may immediately think, yeah, I've done many of these in the past. The easiest way is to find the total current I, right, and then use the current divider formula to find IL, and you would be perfectly right. How do you find I? We have a given voltage. You have to divide it by the total impedance, the equivalent impedance. And what is the equivalent impedance? There is one resistance in series with a combination of two impedances. So if you know how to calculate that equivalent, then you will get the current and you can solve it. Okay, so let me walk you through this. First step, you take the L equals 0.4 millihenries, convert that into XL, which I didn't write the formula here, but you know that XL, the impedance is j omega L, right? So if you take L, the omega is here, 4 into 10 to the power 4, you multiply the 2, you should get 16. So put a j. If it's a capacitance, you put a minus j, right? You remember that. So j, 16 ohms. It's actually minus j by omega c for a capacitance. So the omega c is in the denominator. But for an inductance, the omega L is in the numerator. It's on the top. So I'm directly applying the current divider formula. So for ILT is this resistance divided by this plus this, right? That's the factor, multiplied by I. Now what is I? I'm writing that directly. I'm taking the voltage in phasor form on the top divided by the equivalent impedance, which, like I told you, is the sum of this in series with this combination, which is in parallel. So 20 plus 30 in parallel with J16. So if you solve this, you should get this 1 by 20 plus 30 into J16 by 30 plus J16, which is this parallel combination. And if you simplify that, you get this, and in the denominator this. This whole thing you should be able to put into your calculator and come up with this answer. So IL is 0.75 amps with a minus 98 degrees phase angle behind the voltage. Well, the voltage is at minus 45, this is at minus 98. So between the two, the phase angle is the difference between the two, right? It's about 53, yeah. Okay, all right. So that's how you solve this problem. And that is all that I am going to do in terms of a review of phasors, which is part of this chapter. And that's the end of this chapter. Okay, so that is the first chapter. We are done with it. I don't know, I've got a minute to talk to you about something. What is new and what is important here? I think there's really not too much that should be difficult. Actually, going back, we didn't spend too much time on this stuff, electric field, right? This formula for electric field intensity E, right? And electric flux. But the reason there's not any problems given in the textbook, and also we're going to do much of this later on as we go into the future chapters, so I haven't spent too much time on this, but you should at least know that these formulas are important and we're going to use them in the future. Similarly, there was a force formula that we didn't do much with. There's also the magnetic equivalent of a magnetic flux density. Flux is also called, or magnetic flux density is flux per unit area. So this is only in the case of a single wire with current in it, right? Now there are many more complicated variations on this. You may have a wire that is like a coil, or there may be two wires. So all that we'll do in the future. But in this chapter, all that he has told us is if there is a single wire, then the magnetic field is like this. And the magnetic flux density formula is given. And we are introduced to these things like mu 0, the magnetic permeability of free space, then relative magnetic permeability of materials. So this was stuff that we skipped because we didn't really have too much to do here. Similarly, there's something called magnetic field intensity, H. And then there's force experienced by a charge in the field. All this we can wait to do later. Okay, and then of course we spent enough time on traveling waves and did some problems. Okay, so the important thing, if anything, that you should become familiar with and comfortable with is this fact that previously our sinusoid didn't have the second independent variable, distance or x. It just had one, which was time. Now we have two, but they are both in one equation, and we may have to learn how to manipulate that. That's why we'll do more partial different derivatives, right? When you have two variables, your calculus method is to use not just differentiation but partial derivatives. That's why this whole course depends on your knowledge of partial derivatives, and we'll pick that up in the next 2 or 3 weeks as we start vector analysis. Okay, that's it.